Well, I guess I'll get this thing started. This is not my ideal format, but sadly I forgot to bring my notes. Um, so let's see here. On the course web page, which is here, I talked about this a little bit before, I thought about talking about it some more today, the proof that E is not a rational number here. So I figured we could start video class, with this proof right here. I'll try to go slower through it. Maybe we can appreciate it together. So this is a proof that E is not a rational number. Like I told you guys, it's due to Fourier. And it was the proof I was conjecturing might be possible the other day in our class, but here it is. So suppose E is rational. In other words, it's A over B, where A and B are integers and B is non-zero. Then the genius step here is to define this x, right, which is defined by b factorial times e minus this partial sum of the exponential function. And the thing is, if you multiply b factorial through here, because these n factorials are starting, excuse me, they're only going up to b factorial. There's no number in here which is larger than b factorial, which is to say that when you multiply that out, right? Sorry, I'm trying to, not very good at multitasking. When you multiply that b factorial through, of course, a times b minus 1 factorial there, because the b and the b factorial cancel, they give us b minus 1 factorial. And that's an algebra fact that should be familiar with you guys from like Calc 2, for example. And then this over here, well, you've got these things added together, right? But every one of these, we have at most one, the smallest this could be is 1, right? Every one of these otherwise is actually an honest to goodness integer, supposing that b is, supposing that b is greater than 1, I suppose. Excuse me. Which is the case here. Anyway, so what that all means, if you study this here carefully, we can see that x is an integer because it's the difference of two integers, right? So then what? Well, the whole point of this is to, if we assume that, E is a rational number, then we're going to be able to produce a contradiction, and that's what we're working on here. Okay, so next we give an argument that 0 is less than x is less than 1. So we assume that E is, by definition here, n equals 0 to infinity 1 over n factorial. All right, that's a reasonable definition for the exponential function, and if you put x equals to 1 into that, you get this. So stands to reason this is a good definition for the number E. There's about 5 different definitions you could give for E. Here's one of them. But anyway, so with that in mind, we have x is equal to this. Now we replace the E with its power series definition, and then we have the difference of these two. Just leaves us the tail of the power series, not power series, numerical series, because we're subtracting off the start of it, right? So we're just left with the end, b plus 1 to infinity. But since we have a sum of positive terms, and we already know, of course, that we can prove that this converges, if you like. If you don't believe me, we could use a ratio test or something. So this definitely converges, and as such, if we take a part of a convergent series, which is a sum of positive terms, and of course that's also positive. So there we have now proved that x is a positive number. All right, so thus 0 is less than x. Now, the next part of the argument, we argue that x is less than 1. Part of this argument rests on this estimate right here, so-called upper estimate. And, credits where credit's due. I found this on Wikipedia, and I just wrote it up a little bit from theirs. But this is based on an argument I found on Wikipedia, which is attributed to Fourier. Anyway, so b factorial over n factorial, well, you've got the b factorial piece canceling in the n factorial. It just leaves you with the product of b plus 1, b plus 2, and so forth, right? But that is less than or equal to b plus 1 to the n minus b terms. The reason for that is in this product of numbers here, b plus 1 is the smallest. So if I would make the numerator the product of numbers which are smaller than every factor, and we're making the numerator in total, and making the numerator smaller, right, which makes the fraction larger, and as such we get estimate star. Right, and indeed this inequality is actually strict as long as we have n is greater than or equal to b plus 2. Right, which would mean that there is at least one smaller factor here. All right, and okay, so let's go on. So I kind of hurried through this the other day. I wanted to kind of like stop and dwell on it, because I think if we're smart about this, maybe we could use this proof to prove, like, maybe we could prove the irrationality of pi with this. Maybe we could prove the irrationality of the natural log of 2 with this if we modify this proof a bit. I have an idea about how to do that. Maybe we can do that. So I wanted you guys to understand this proof. And so it's going to take some time, and that's what we're doing. So let's see here. If we have k equals n minus b, then we can change the index of summation from this to that down here. All right, so like n equals b plus 1. So first of all, that's the star estimate for a comparison. So you have the sum of positive terms, which is bounded above by this other sum of positive terms by comparison test. And I mean, ultimately, comparison test rests on the thing we're comparing to actually also converging in this context with the application of the theorem. But the steps which are below will ultimately show that the larger the larger series which we're comparing to indeed does converge. Okay, anyway, so we have this inequality here. I change the summation from n to k equals 1 to infinity of 1 over b plus 1 to the k. But at this point, I'm like, oh, I know what that is. That's a geometric series, right? And geometric series, we know how to sum a geometric series. In fact, we worked that out in class even in this course, if I recall correctly. So identify that the leading term is the a is equal to 1 over b plus 1, and the ratio of the geometric series is 1 over b plus 1, which is by assumption, uh-oh, the light bulb by my head has just went zzz. What's going on here? So the ratio is 1 over b plus 1, and so that's less than 1 here, which means the geometric series converges to, a times 1 over 1 minus r, which is this. But then when we do the algebra, we get 1 over b, but remember b was a positive integer here, larger than 1 in this context. And as such that, by the way, if b was equal to 1, if you go back to the original, e equals to a over b, then that would mean that the exponential is an integer, but that's just clearly false. Maybe we need to give a separate argument for that case. Truth be told, I should probably be more leery of the proof in that particular context. Maybe there's a gap in this proof I need to prove. In the case that b equals to 1, there's a separate argument, perhaps. But anyway, setting aside that worry, we have that 1 over b is less than or equal to 1. And in fact, this is a strict inequality if you go back, because there's an inequality up here which was strict, right? Oh man, up right there, yeah, right there. See that? All right, so we have x as an integer, which is between 0 and 1, but there is no such number. Therefore, there does not exist an a and b for which e is a over b. So we conclude that e is in fact not a rational number. So there you go. There's a slow, well, as slow as I can go, proof that e is irrational. And I do think we could modify this proof a little bit to prove like natural log of 2 was irrational. I claim that in a message to you guys for a particular homework we were working before. And like also pi is irrational. So if you think about this proof, like what are you going to need to do to prove, natural log of 2 was irrational or pi is irrational? Well, like first order of business is you're going to have to find, the analog of this animal right here, right? A definition for for those other numbers, which is based on a series, right? So for natural log of 2, I would use the alternating harmonic series for that one. 1 minus 1/2 plus 1/3 and so forth. I know that converges to log 2. That would be my natural inclination there. For pi, there's various options. One might be inverse tangent of 1. It's fairly easy to find the power series for inverse tangent of x, and so that would give us a natural whatchamacallit, series to define pi over 4, and we could kind of go from there. So those are ideas I have. All right, so continuing here, excuse me. So sorry we didn't have class in person today. It's kind of annoying, but I'll do my best with putting something together here. I wanted to try to hit a couple different things, so I'm just going to kind of go back to the notes and pick up some little pieces here and there I missed. The first of which I suppose is, we'll just look at this. I kind of skipped over this. Let's talk about this one here. All right, so this is example 3.34, I think. And I mentioned that technically the current typed versions aren't quite right because I needed to define a sub 1 over n in order for it to be like reasonable. Get some more light here maybe. Whee! All right, so here it is. N equals 1 to infinity of a sub n. I'm claiming that's 0 to infinity if we go 0 to n. And I'm going to define a sub 1 over n to be 0, 1 over n for n greater than or equal to 2, natural number. And I suggest that we should use the floor function like we defined in class, right? And you guys helped me construct the ceiling function in class too. That was great. But I think we just need the floor function for this one. Okay, so like why is 0, 1 a subset? Let me zoom in a bit more. Oop, too much. All right, there we go. So why is 0, 1 a subset of this union? So if we let x be in the interval of 0 to 1, that means that either x is equal to 0 or x is between 0 and 1, right? Now if x is equal to 0, then clearly x is an element of 0 to 1. Well, I mean, that's what I'm assuming. Let me not be an idiot. Well, 0, 1, though, is equal to a1, 1 over 1. Or if you like, just... So I meant to say there, or what I really should say there is just a sub 1. All right, fine. Hence, it is in the union. Oh, rats. All right, fine. I guess I have to make it n greater than or equal to 1. Fair enough. I guess it's good I'm going through this, isn't it? Let's see here. So, because otherwise I haven't defined a sub 1 over 1 there, I suppose. Fine. You should be picky like this, though, all right? So, let's see here. Where was I? So I'm trying to prove that this is a subset of a... Oh, I'm working on this one. All right. I think I proved this one in class, actually. Which is your homework problem. Sorry. Try not to do your homework in class. My bad. Anyway, so here, this particular alleged subset, 0, 1 is a subset to this union. So first of all, if x is equal to 0, then x is, of course, an element of a sub 1 over 1. Fine. All right, I'll make up my mind eventually here, guys. Okay, so that was fine. All right, let me go on here. Otherwise, x is not equal to 0, and so that means x is somewhere between 0 and 1. But then 1 over x is greater than 1. And if we let n be the floor of 1 over x, then it's, by construction, less than 1 over x. Since 1 over x is not an integer, right? If x is between 0 and 1, then it should be clear that x is not an integer because, right, there's no integers between 0 and 1. Now, thus n is a natural number and 1 over x is greater than n, which means that x is less than 1 over n, if we flip that around, and therefore x is an element of the subset 0 to 1 over n, which we define to be a sub 1 over n. And so, since x is in one of these guys, it's in the union of all of them. Therefore, we find that 0, 1 is a subset of the union. Because we took an arbitrary point in 0, 1, and we showed that whether that arbitrary point was 0 or a number between 0 and 1, in either case, we have it's an element of one of these a sub 1 over n sets, which suffices to prove that, excuse me, it's in the union. All right. Now, on the other hand, if we pick x in the union, then that means that there exists, there exists a sub 1 over k, which contains x for some k. That is to say that x is an element of a sub 1 over k, which means that 0 is less than or equal to x is less than 1 over k, but 1 over k is less than or equal to 1. So this means that 0 is less than x is less than this, which is less than or equal to 1, which of course, because that inequality is strict, gives us that 0 is less than or equal to x is less than or equal to 1, but that, by definition of interval, means that x is an element of 0 to 1. So we find then that this union is a subset of that, because an arbitrary point in here was also found to be in there. And then finally, using double containment, we conclude that these two sets are equal. The proof that this is probably much easier, I leave it to the reader, is a factually inaccurate sentence. I didn't leave it to the reader. I proved that in class. So I'm sorry about that. Anyway, let's see here. What's up next? Let's see here. I think we've talked about all these things here. Talked to you guys about topology in the last video a bit. Over here, this definition isn't quite right. So let me write that one out by hand again. I can find some paper. So let's fix this. I just wanted to talk about what is a metric. All right. So this is just another definition that I want you guys to be aware of, for the sake of. So I'm trying to put some words in your mind so that when you come back to them in other courses, that it's not the first time you've seen it. So this is a definition. A metric or distance function all right, on a space M. So a space is just a word I'm using somewhat ambiguously. It's a set, all right? A space is a set. Is a function. Oh no. See, I'm already getting the cart ahead of the horse a bit, because we haven't defined function in here yet. But it is a function from the Cartesian product of the set with itself. Right? We know what Cartesian product means now, right? And it takes its outputs, its values, in the real numbers. All right, and it satisfies the following criteria, such that 1, it's positive definite. So we have d of x comma y greater than or equal to 0, and d of x comma y equals to 0 if and only if x equals to y. So the distance between 2 points is 0 only if those 2 points in fact are the same point. This collectively is positive definite. It's also symmetric, so d of the distance from x to y is equal to the distance from y to x. That's the symmetric condition. This up here was positive definite. And then case 3, which I have mangled in the notes as well, is it satisfies the triangle inequality. So the distance from x to y plus the distance from y to z is in fact greater than or equal to the distance from x to z. So the reason that's called the triangle inequality is somewhat self-evident once you draw a picture. Now I'll draw a picture as if the space is, higher dimensional. Although you should notice that the word dimensional, when did we define dimensional? What does that even mean? That's something you should ask and expect an answer for eventually in mathematics, right? What do we mean by dimension? Maybe you've got an intuitive idea about what that means already, but it does warrant an actual definition, right? I'll just tell you, I'll spoil the story for you. The definition of dimension is given in linear algebra. Once we define what's called a basis for a vector space, then we can define the dimension of a subset. But the meaning of dimension is more general than that. So basically something has dimension k if there's a one-to-one bijective correspondence between that thing and k-dimensional Euclidean space. But anyway, whatever that means. So this is x, this is y, this is z. So the distance from x to y, we could look at as the length of, for my picture here, this line segment, right? So that distance, and then the distance from y to z, oh man, these markers got wet, is that distance here. Well, that's kind of I try to dry this thing off, but this is going to make the whole stack of paper wet if I'm not careful. There's that distance, and then of course the distance from z to x is this distance, and of course this distance has to be smaller than or equal to those two distances, right? Any definition for the distance between 2 points that's going to be reasonable, it should be based on something like that. Now there are some, so the concept of a distance is up for grabs. So let me just talk about m equals to r2 for just a second here, tell you about different notions of distance. The standard notion of distance, of course, that you guys have already been taught, hopefully, is the distance between 2 points is Euclidean distance, right? So we have x1 minus y1 squared plus x2 minus y2 squared, right? That gives us the Euclidean distance. So this is the so-called Euclidean distance function. So, or you could call it the standard distance on the plane. But there are other definitions, there's I could call that d sub 2 maybe. D sub 1, the distance between 2 points in the one metric would be the absolute value of x1 minus y1 plus the absolute value of x2 minus y2. So you just add together the absolute values of the differences. That's another definition of distance function. You could also take, instead of taking the square root of squares, you could take the pth root of pth powers, like this. All right, and so pth root. You can work it out that all of these different functions, they all satisfy the axiom for a distance function. So these define competing notions of distance on the plane. All right, and yeah. So that's kind of neat. Of course, then you can ask more interesting questions like, what's a circle look like in these different notions of distance, right? So if you have a metric space, you could define a circle. What would you, well, maybe it could be a good definition of circle centered at the origin. How about this? Definition. Circle centered at origin. In metric space. So we'll say, usually we refer to the metric space as a pair. It's a space paired with the metric d, is something like this, right? X in the metric space. Sorry, I'm off the page, my bad. I'm sorry, guys. There it is. circle centered at the origin in metric space MD is this collection of points x and m such that the distance from, I said origin, so apparently zero's in the space, right? Distance from x to the origin, and let me make it more specific here, unit circle, all right, unit circle, equals to 1, right? And so this would define a circle, and in this space. And so, like, if we look at that being the definition of circle, a set of points equidistant from the origin, it's the unit circle. You get different shapes for these different cases, and if you look into it, you get like let's see here. Of course, you know the regular circle is the Euclidean circle, of course, the set of points that sum squares is 1. But if you look at like the one words here, guys, the one circle. Oof, this marker is toast. Sorry, I got some bad markers in here. The one circle is just a diamond like that, and if you were to look at the cube root of the sums of the cube, I need absolute value here, I forgot. Otherwise you got negative numbers for odd p. So absolute value here, my bad. Absolute value. That gets you, like, should make my picture bigger. Oh well. It kind of blows the circle up a little bit. So like the cube is like out here somewhere. So kind of like if you can imagine the circle kind of blowing out its cheeks like a trumpet player or whatever. And anyway, if you take the limit as p goes to infinity, you get a square here. So the circle becomes a square in the limit as p. If you think about this limit, whatever that would mean, if you think about p becoming arbitrarily large, you get a square for your circle. You know, and the square in our current Cartesian product notation would be -1 squared, right? Because these points, it's like 1, 1. This point down here would be -1, -1. All right. And this is in that limit, it's actually the square. So, all right, my point to you is simply this, is that the notion of distance is perhaps more abstract than you realized. There's like a lot of different notions for distance, and actually each one of these different notions for distance we can use to define a topology, where we use the metric, like the open, that idea about like an open ball, and we use those to generate open sets. But anyway, hey, I'm getting too far into the weeds. Leave that for a future course. I just wanted to make you guys aware of some of these ideas. So I think I've done enough damage to the ideas. Let's go on here. Sorry about the typos in the notes again. One interesting one exceedingly silly metric that you could give that's kind of fun to think about. So one final example here. I'll try to squeeze it into the page. Next page, actually. So a rather silly metric is if M is a space, then we'll define the distance from x to y to be case-wise defined 0 if x is equal to y, and 1 if x is not equal to y. This is a very silly metric. It says that the distance between any point to itself is 0, and the distance between any other 2 points is 1. And I mean, it's like, wait, what? Well, yeah, but the thing is, if you go back and you work through it, you'll find actually that this, in fact, satisfies the 3 axioms for a metric. This is an honest-to-goodness metric. And so if I... well, let me just... I probably should save this for a homework problem or something, but you can define open balls with respect to this metric, and I think we can get I think this ends up giving us the discrete topology if we work through it. But anyway, I don't have that I'll try to make that into a problem or something at some point so you guys can appreciate the details there. But all right, enough about that. This is just kind of a weird example, an even weirder example. Enough weird examples. Let's get back to set theory. Let's see here. So one of the examples I have in the notes that we should probably just sit and look at for a second here is the concept of a Cartesian product is, like I said, used out throughout calculus, higher math as well. We can think about a space S, then the space Cartesian product with 0, 1. We can think of as a cylinder, which each cross section is like S. Or we can think of S cross 0, 1 as a space formed by gluing a copy of S at each point along the unit interval. If we let S1 be the unit circle in R2, then, by the way, S1 cross S1 is called a 2 torus, which is technically speaking a subset of R4 in their current formulation. Anyway, more to the point is you'll see Cartesian products used to build examples and further sets. Now I think I can draw a picture of what I was just talking about there. So like, let's see here. Let's go like this. Let's suppose this is my unit circle, right? That was supposed to be a unit circle. All right. Oops. Let me zoom out a bit. I'm not a good cameraman. Let's see here. So, that's a horrible circle. But anyway, so if that's S1, you can think about the Cartesian product in some sense as like just gluing on like here I'm gluing on a unit interval like that. So, excuse me. So here I'm thinking I is 0 to 1, right? So if I do S1 Cartesian product 0, 1, what that would mean is like pairs x comma, let's call it z, such that x is in S1 and z is an element 0 to 1. Right, now expanding that a bit, we could think of that as really and so here's one of those places where I'm going to identify a pair of a pair with the triple. So x is in S1, which is really to say you've got like a, x1 comma x2 perhaps, and z, right? Such that what? Such that, well, x1 and x2 are real numbers, and we have that x1 squared plus x2 squared is equal to 1. They're on a circle, right? And 0 is less than or equal to z is less than or equal to 1. All right. So so I'll draw another. Well, let me not. So anyway, if I was to repicture this set I'm building using Cartesian product, right? What I have here is just a little like cylinder without a cap, right? It's got no caps. It's just the just the side of the can, not the caps, right? If I wanted to add caps to it, I'd have to union something else to it, right? Like, so if I call this whole thing M, right? So here's my M. If I wanted to say add in the caps, I would say let's let D be say x1, x2 in R2, such that x1 squared plus x2 squared less than or equal to 1. So that would be the unit disk in R2. And so if I took that, and if I look at like D Cartesian product with the set just containing 1, all right, well that's the top cap, which I'll call I'll call it M top. All right, and I'll draw a picture there. What am I? That set is, oh man, this stupid marker. Get so much water in this thing. That's this piece up here, right? That would be the top cap, right? On the other hand, if I wanted to, construct the bottom cap, the base of this, we want to close the cylinder, right? Give it a bottom. I could do D Cartesian product 0, and that would be the set of triples rather, in R3 that you need to put down there at the bottom, right? Yeah, so I mean, we could do other things. Let me do another example. Maybe this is helpful. I don't know. I wanted to do more of these in class, and we got into the more into doing stuff with those arbitrary unions and so forth, which are good, but maybe a little bit more of this is good. Also, all right. So how about excuse me. I just had an idea. We could maybe learn something together with this. What if we build, example 2 here. We could let S be like for square. And this could be, let's say, 0, 1, Cartesian product 0, 1, like that, right? So this is the unit square, right? And then I could look at something like, let's see here, I could do like, sorry guys, I'm thinking here. I guess I'll draw a picture to try to show you where my thought process is going. I'm trying to build the cube using this, all right? So the unit cube, centered at the origin like so. All right. So you got 6 sides that you got to come up with, right? So I think I can do these. I can do these 2 at a time. I think I can figure out how to do them 2 at a time, right? So like, let's call this face 1. In the back, face 2. On the side, face 3. On the back over here, face 4. On the top, face 5. On the bottom, face 6. All right, so I don't know if that's clear or not. It should become more clear as I write the formulas. All right. All right, so let's try this out. So here's, x1, x1, x2, x3 if we're thinking in that kind of notation. Great. So to pick up the face 1 and face 2, those are in this, like the front face is at x1 equals to 1, and the back is at x1 equal to 0. So if I do like 0, 1 Cartesian product with my square, that will give me F1 unioned with F2 actually. And then if I do, let's see here, to get faces 3 and 4 here and here, that's where we have let's see here, that's where we have x2 equal to 0 and x2 equal to 1. I can't do this again. I guess I'll have to do well, I'm not sure this is really very helpful, but I'll do 0, 1 Cartesian product the set 0, 1 Cartesian product 0, 1. So that what this does is, if I can write this out in detail, it is x1, x2, x3, such that x2 is equal to either 0 or 1, and 0 is less than or equal to x1 and x3, which is less than or equal to 1. All right, there's that. F2, this one would have been x1, x2, x3, such that we have x1 equal to 0 or 1, and 0 less than or equal to x2 and x3 less than or equal to 1. All right, that one. Now, the other two here, faces, so this was what? This was face 3 and 4. Face 3 union face 4. So now we got face 5 union with face 6. Let's see if I can build that using my square again. Maybe, maybe not. Let's see here, 5 and 6, the top and the bottom, right? So I think that one I can do like the square Cartesian product with, again, the set 0 and 1, but this time playing the role for x3. So specifically, that's going to be x1, x2, and x3, such that, x3 is equal to 0 or 1, and 0 is less than or equal to x1 and x2, which are less than or equal to 1. So that's that's the top and the bottom faces here of this cube, right? So if we want all of the faces of the cube, we take the union of all of these, right? F1 union F2 union F3 union F4 union F5 union of F6. This is what is this? This is the all the faces of the cube, right? Now if I want to talk about the solid cube, right? What's the solid cube? That's easier, right? So the solid cube, we can just do 0, 1, Cartesian product 0, 1, Cartesian product 0, 1, or if you like, that is the Cartesian product of 0, 1 cubed. It's 3. And what that is x1, x2, x3, such that 0 is less than or equal to x1, x2, and x3, less than or equal to 1. But this is of course the edge of the cube, right? The so-called boundary of the cube. So if I this, I don't require you to know this in here necessarily, but this is what's called the notation that we would tend to use in like Calc 3 maybe would be something like this. This is the boundary of 0, 1 cubed. All right, it's the edge of that set. All right, so anyways, an example. I just thought I would, maybe that's a good laboratory to see a little bit more with what we can do with Cartesian products. Hope that helps you. So now I have some select reading from Proof, Logic, and Conjecture, the Mathematician's Toolbox. And so these are some things I wanted to look at in here because he has some nice, careful statements of things that I think are good for us to look at. And some of you keep asking me about this, so it's probably good for us to talk about it a little bit. Because those are right and good questions to ask in this course, and they should be responded to more systematically. So here's an attempt at that. So this is theorem 5.1, which is Russell's paradox, and it says simply this: naive set theory is inconsistent, that is, it leads to a contradiction. So the paragraph above talks about the fact that this paradox is actually worse than paradox. Now, a paradox, technically speaking, is a seeming contradiction. Russell's paradox is not a seeming contradiction, it's an honest-to-goodness contradiction, which is worse. Right? Examples of like paradox in the proper use of the word would be like the twin paradox. That's a seeming contradiction of special relativity. That's not an actual contradiction. There are others, but okay. So here it is. Naive set theory is inconsistent. That is, it leads to a contradiction. The proof is just this. And the core of it is a single use of the comprehension axiom, which is that if you can describe a set, it's a set, all right? So to form the set of all sets, so what we do is form the set of all sets that are not members of themselves, all right? In symbols, A is equal to B such that B is not an element of B. All right, so it's a set of all sets which are not members of themselves. And then we simply ask the question, is A a member of itself? All right, well, if A is an A, then by definition of it, A is not an element of A. All right, on the other hand, if A is not an element of A, since A is a set, we must have that A is an element of A. So we've proved it's both an element of A and not an element of A, which of course is a contradiction. So this is the set theoretic analog of the thing I read you guys, the barber's paradox. With, in a certain town, there's a single barber who is a man. Barber shaves all men in the town who do not shave themselves, and only those men. So it's the same thing as this right here. And so this contradiction, is dealt with in the Zermelo-Fraenkel set theory through playing with what's allowed to be elements and sets and so forth. Again, I don't want to get into all that, but there's a good breakdown of the some of the things that come as a result of that. So he says, the discovery of the paradoxes of naive set theory through the foundations of mathematics for a loop. The mathematical theory that leads to contradictions is of no use, of course. So are other branches of mathematics consistent if they're based on this uncertain set theory, right? So in conclusion, the comprehension axiom is actually the culprit because it's just too general. So the revised set theory that is currently used keeps the original extensionality axiom, which is to say that two sets are equal if they have the same elements, but it replaces the comprehension axiom with about a half a dozen more specific rules postulating the existence of various sets. So the most widely used version of modern set theory was developed by Ernst Zermelo and Abraham Fraenkel, called Zermelo-Fraenkel set theory, or ZF set theory. And if you look at Appendix 1 of this book, he essentially has the axioms for ZFC set theory. So did Zermelo-Fraenkel ever prove that it's a consistent theory of a consistent set theory? Well, no, they didn't do that. And in fact, it has been proved by Gödel that any theory which essentially contains arithmetic is necessarily containing statements which can neither be proved true or false. And so that's you got to be careful about meaning of words and so forth in that context. But again, all of Gödel's stuff also actually involves these kind of self-referential arguments, which are at the heart of the Russell paradox. So I think a lot of this story has kind of played out, but there is probably an open question here which may or may not have sweeping consequences for all of mathematics. It's kind of like the dominant thought processes of most mathematicians is there's nothing to worry about here, nothing to see here. It's been fine for a century, but well, we'll see. So another way to talk about this is there's not a single set theory. There are actually more than one possible set theories. And this I thought I also should show you is a proof from page 145 in Wolf. And this is a better example of a biconditional proof than I gave you guys. So like I did a biconditional proof, so first of all, his arrow both directions is my double. I put 2 lines, he just puts 1 line. I always put 2 lines, so I'm not going to stop for your class. So these are all biconditionals. And so he's giving a proof using extensionality that these 2 sets have the same elements to prove that these sets are equal, which is fine. The improvement in his argument here over the one I showed you in class, I think last class, was he's actually put the reasons in each step over here, and that's a better practice. That would be a better proof than what I gave you in class. So, if I ask you for I may say something like, if you use a biconditional proof of set equality, make sure you comment each step. That's what I'm talking about here. So let me just get into it. X is an element of this union with this intersection if X is an element of A, or X is an element of B intersects C. Well, that's the definition of union. Excellent, right? Excellent. So this right here, it means X is an element of A, or X is an element of B, and X is an element of C. Notice the use of parentheses here. That's, I think, an improvement. I don't know if I had parentheses in some of what I wrote, like I was just using grammar which is much shakier. Parentheses are nice. All right, so definition of intersection. Then, to go from here to here, he relies on tautology 30. Now, tautology 30 is part of a list of tautologies that he has earlier in the book, which I will try to go find. So again, my notes are somewhat based on this book, and so I think this is a very excellent and careful book. I have much praise for this book. I would like to use this book for the textbook of this class next time. But if you go back in on page 37, his list of useful tautologies on that, in 30, at the bottom of the page down here, he has distributive law. P or Q and R, if and only if P or Q and P or R. Now we prove these kinds of tautologies using truth tables, right? So I obviously, when I proved that thing last class, I didn't refer to a tautology. I just said by logic, right? So that's not as excellent as this proof. This proof is better than mine last class for sure. Although I don't think I proved this last class, but it was like this. All right, so that's by tautology 30, and then what you've got is, okay, so X is in A or X is in B, which means X is in the union. X is in A or X is in C, which means X is in that union. So by definition of union, we get this step. So these comments over here are referring to the step which was just taken, right? So like going from here to here, that's the reason. Going from here to here, that's the reason. Here to here, that's the reason. That's the custom here. Going from here to here, that's the reason. All right. Here to here, we have what? X is in this and that, which means it's in the intersection that. So because each one of these is a biconditional, transitivity of biconditionals, we then have X is in here if and only if X is in there, which is to say that they're two sets with the same elements. And then in here, he's like applying UG and extensionality. So he has labeled the extensionality axioms at UG. All right, so I thought it would be good for us to look at that proof. Now you've seen it. Let's see here. Yeah. Let's see if I have anything else to tell you guys. He has a theorem for power sets, I think that's a little bit... I don't think I have this in the notes. It's kind of interesting. This would be fun to work through, right? The power set of an intersection is the intersection of the power sets. A equals B if and only if the power set of A equals the power of B. A is a subset of B if and only if the power set of A is a subset of the power set of B. A is a properly contained subset of B if and only if the power set of A is a properly contained subset of B. So that's a neat little theorem there, which I think I don't have in the notes, and so it'd probably be good for us to prove something in there. Let's see. Maybe we should do that. Anyway, and then, but yeah, I think I'm trying to remember if there's anything else I was going to show you guys. That might be it. Oh, also his discussion of the Cantor set's pretty cool. I haven't showed you guys the Cantor set yet. Let's look at that for a second. We'll end class a little bit early today, since after all there's no class. Excuse me. The Cantor set, also known as Cantor's discontinuum, is a set of real numbers that's important to higher mathematics. And to define the Cantor set, you start with a closed interval 0, 1, and then you delete the middle third. So like A1 is the middle third of the open interval 0 to 1. And then A2, you delete the middle third of what's left. So 1/9 to 2/9, 7/9 to 8/9. And then step 3, you delete the middle third of what is still left, which is this. And then the Cantor set, I'll show you the pictures here in just a second. The Cantor set is what you get from removing all of these from the set 0 to 1. And this Cantor set has interesting features, actually. as it happens. Notice that it's built just using rational numbers. It's like you start with the unit interval, take out the middle third, then take out the middle third and the other remaining middle thirds. That's step 2, I suppose. Step 3 starts to get hard to picture. So we took out the middle third of these guys. Take the middle third of these guys out. Deleted, 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 deleted. And so then you're left with this and that 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 from 0, 1, right? And then next step is you're going to delete the middle third of each one of these guys, of the sets that remain. And this goes on forever and ever. And this what's left is defined to be the Cantor set. So notice that the Cantor set is built just using rational numbers, and so there's something there. Anyway, it turns out, and believe it or not, you can use this Cantor set to construct the real number system. In part, it deals with the continuum aspect. So to get so just to give you a quick sketch, to build natural numbers, we can use the empty set and build something called the successor function. It's not obvious, but it can be done. Then to get integers, you look at equivalence classes of whatever that means. We'll learn soon in this semester, but a little bit later. You look at differences of whole numbers to get the integers. Then once you have integers, of course, we can build rational numbers as fractions. We've talked about that some. And then past that, how do you get like the irrational numbers? Well, there's 2 ways. The one way is with analysis, using something called the completion. You can adjoin the limits of all Cauchy sequences in your space. This is called the completion. And then the other way, which is perhaps a little bit more concrete, is you can use these so-called Dedekind cuts, which are, in some sense or another, based on this Cantor set construction. But I don't know the Dedekind stuff very well. If it's going to be covered anywhere, it'll probably be covered in like Math 431. So certainly you're not required to, there's nothing here that's required of you. What I require of you is to be able to do problems, again, Proof, Logic, and Conjecture, Mathematician's Toolbox by Wolf, great book. Way better than my notes, I think. But on the other hand, my notes are probably closer to the course. So here's your homework that you hopefully are done with, because it was supposed to be collected about an hour ago. Oh well. But anyway, you are responsible for being able to work problems like these, right? So now, problem 39, it's a doozy. I hopefully will have a solution written up for you guys sometime soon of that. So Thursday, what's going to happen is, if the snow clears up and we have class, great, I'll collect mission 3, and we'll talk about any questions that you guys still have about the test, which is coming up next Tuesday. And then if there isn't class Thursday, well, I'll figure something out. I don't know what it is yet, but hopefully that won't happen. But anyway, thanks guys.